To fully characterize the adhesive, it's also important to discuss the environmental and loading conditions that will be seen in Module 16. Okay, so we have seen the failure strength test, the fracture energy tests. What about the environmental and loading conditions? That's what we are going to see now. Starting with temperature, you have here a graph that shows the stress or shear stress versus shear strain for an adhesive tested at various temperatures from minus 55 up to 200 degrees C. As you can see, we are talking about different words. Here very stiff, very strong, and here extremely weak. I have to tell you that the TG of the adhesive is about 150, so at 200 we are well over. It's not a structural adhesive anymore. From minus 55 up to 100, there is a big variation of stiffness, strength, and ductility. So really, in joint design, you have to take this into account if you have to have a proper estimation of the failure load. What about the variation of the fracture energy as a function of temperature? Well, curiously, there is not too much variation below TG. As you can see, you have a graph here where you have the fracture energy in mode 1 versus temperature. TG is about 175 or something like that, or close to that. And you can see that the fracture energy is more or less constant below TG. We can look back at the previous graph to understand this, because fracture energy, an estimate of the fracture energy, can be seen as the area under the stress strain curve. And if you look at this area and this area and this area, well, they don't differ that much. That's what the fracture energy also doesn't differ that much when you are below TG. What about water? What is the influence of water in the adhesive? Well, the water will ingress into the adhesive, it will diffuse, it will penetrate into the adhesive. It doesn't stay at the surface like metals that corrode. No, they go inside the adhesive. So first of all, you need to know how fast the water ingresses. And this is done with diffusion tests. You weigh the adhesive in water at periodic intervals, and then you reproduce the results in a graph, weight gain versus time. And you have a graph like this that allows you to determine the diffusion coefficient that will tell you how fast the water goes in. Well, with this, you can already predict how fast the water will ingress, but what you also need is to understand how the water will affect the adhesive properties. So you need to do mechanical tests as a function of the amount of water into the adhesive. That's what is represented here. You have the stress versus strain for various periods of aging. Here is without water, aged at 120, nearly 300, and nearly 500, with different amounts of water. As you can see, the strength drops, the ductility increases, and the stiffness also drops, which is not too bad. A bit of ductility or an increased ductility is good. You will see that into joint design. And also, if you dry the adhesive, you can go back here. There is only physical aging. The problem is that when you have chemical aging, when you have chemical change in the structure caused by water, it's called hydrolysis. In that case, you cannot go back if you dry the adhesive. It's a permanent damage. In terms of fracture energy, you have here some results. Again, fracture energy in mode 1. For the unaged and aged conditions, you can see that there is a drop. You have here the failure surface. The failure tends to go a bit more to the interface when you have the presence of water. But clearly, there is a change in fracture energy. Now, what about the strain rate, the test speed? If you load the adhesive very slowly, you have a result. But if you load very rapidly, you have another result. It's very sensitive to the strain rate. You have here, for the same adhesive, two stress-strain curves, stress versus strain, one obtained at 1 millimeter per minute, and the other one obtained at 100 millimeter per minute. Can you see the difference? It's incredible, the increase in strength and the decrease in ductility. So really, again, you have to take into account the effect of the strain rate. Here in this graph, you have fracture envelopes obtained for various strain rates. Mode 1 versus mode 2, this is a strain rate, and this direction, the strain rate increase. So you can see how the fracture envelope changes as a function of strain rate. Again, a big impact in the mechanical properties. In this chart, it's interesting to see how or which experimental method is adapted for a particular strain rate. You have here different situations, real situations, and the type of test that is recommended for the corresponding strain rate, from hydraulic testing machine up to split Hopkinson bar apparatus. Let's talk a bit about what exists in terms of apparatus. You have here the drop weight. This is very commonly used. We are talking about 3-4 meters per second, already useful in many impact situations. If you want to go for higher test speeds, like a crash in a car or something like that, you can go for the split Hopkinson pressure bar. This is a special apparatus that is developed in the lab, not only for tension, but also with the compression. You have basically two bars, an incident bar and the transmitter bar. The specimen is between, and with strain gauge you can detect or measure the strain waves and have like this the stress strain curve of the specimen.
A split Hopkinson pressure bar is a machine that tests materials at high strain rates. In it, an actuator launches a striker bar, which impacts an input bar, and during that impact, a stress wave is generated that propagates towards the material being tested. When said wave reaches the material, part of the wave is reflected backwards, and part of the wave is transmitted to the specimen of the material and to the output part. Strain gauges are placed in both bars and measure these waves. And with these measurements, we can estimate the behavior of the material being tested. This split Hopkinson pressure bar was specially designed to perform tensile and compressive tests. To achieve this, we've developed a pneumatic actuator that can move in both directions and can attain a velocity of 90 km per hour in a fraction of a second. Given that this requires a high amount of energy, we've developed a special braking system where a lever converts the velocity into force, and a spring set up with shock absorbers will absorb the remaining energy until reaching a full stop.
One very common specimen used in impact situation is wedge impact peel, especially in the automotive industry. You have here an image of the specimen and how it is loaded. So you have a kind of an impact here, wedge, and this will impact in this case it's a pendulum, but it can be another device. It will impact here the wedge and load here the specimen under peel. And you can, like this, assess the capacity of the adhesive to absorb energy. Not only the adhesive, actually, because when you have an impact here, the metal also will deform plastically. In fact, what absorbs most of the energy is the plastic deformation of the metal. And this is clearly seen in this picture. You have here three different situations. It's a tubular specimen, bonded. You have here the use of a brittle epoxy, the use of a spot welds, and the use of a toughened epoxy. The geometry is exactly the same, the loading, and it's an impact, it's exactly the same. When you have a brittle epoxy, you have a premature failure, and there is nearly no deformation of the metal. When you use spot welds, there is plastic deformation, but it's not very uniform and a nice folding. When you have a crush-resistant adhesive, can you see how the folding is nice and the metal can absorb progressively the plastic or the energy by plastic deformation. It's not really the adhesive that is deforming plastically, it's the metal, and it's the metal that is absorbing the energy. But the adhesive needs to keep the metal in position so that it can absorb the plastic or the energy by plastic deformation. You have here a test that we carried out in the lab. It's an impact test of a real component. We tested different types of adhesives from epoxy up to polyurethanes, and the ones that behaved better are the ones that could keep the two parts together so that they can absorb the energy by plastic deformation. So we finish here this module. The environmental conditions, the durability, really these are very, very important topics, especially in the transport industry.